In this video, let's learn about the principles of measure theory in modern finance. The evolution of quantitative finance from rudimentary models to the sophisticated frameworks that govern modern markets was not merely an incremental process. It was a revolution needed by the profound limitations of classical mathematical tools. The journey into the abstract world of measure theory was not an academic indulgence but a pragmatic response to the fundamental crisis. The language of classical probability and calculus was inadequate to describe the complex, continuous, and uncertain reality of financial markets. To understand why measure theory is now the indispensable bedrock of the field, one must first appreciate the failures of the frameworks it replaced. Now, let's look into the limits of classical probability. The origins of probability theory lie in analyzing games of chance, scenarios involving discrete countable outcomes, like a roll of a die or a flip of a coin. The classical definition of probability, elegant in its simplicity, is predicated on this finite world. It defines the probability of an event, A, as the ratio of number of favorable outcomes to the total number of possible outcomes under the crucial assumption that all outcomes are equally likely. This framework, while powerful for combinatorics, collapses when confronted with the realities of financial markets. The first and most glaring failure arises from the nature of sample space. The price of a stock, an interest rate, or an exchange rate is not a discrete entity. It is a continuous variable that can take on any non-negative real number within a given range. This means the sample space of possible asset prices is uncountable. The classical formula, which relies on counting a finite number of outcomes n, becomes meaningless when n is infinite. This will tend the probability to zero. The framework's reliance on finite or countably infinite sample spaces renders it fundamentally incompatible with the continuous phenomena central to the finance. The second fatal law is the assumption of equally likely outcomes. The assumption may hold for a fair die, but is completely false in the case of financial markets. A stock is not equally likely to double its price as it is to fall to zero. Market dynamics, economic conditions, and investor sentiment create complex non-uniform probability distributions. The very essence of financial analysis is to understand and quantify these non-uniform likelihoods. A theory that cannot distinguish between probable and improbable outcomes is of no practical use for risk management, portfolio optimization, or asset pricing. These limitations are not minor technicalities. They represent a fundamental mismatch between the mathematical tool. Classical probability theory is built for a discrete world of countable possibilities. Financial markets operate in a continuous world of uncountable, non-uniformly distributed outcomes. This foundational incompatibility brought the need for a complete overhaul of the probabilistic framework, forcing a move towards a more general and powerful theory capable of handling uncountable sets and arbitrary distributions. This new framework is precisely what measure-theoretic probability provides. Now, just as classical probability fails to describe the space of financial outcomes, the standard tool of integral calculus, the Riemann integral, fails to reliably compute their expected values. In finance, the price of a derivative security is fundamentally linked to the expected value of its future payoff, discounted to the present day. In a continuous setting, the Riemann integral, familiar from introductory calculus, attempts to calculate this value by partitioning the domain of the function into a series of small vertical rectangles and summing their areas. This method works well for well-behaved continuous functions. However, the payoffs of financial derivatives are frequently anything but continuous. Consider a simple digital option. Pays a fixed amount, say $1, if the underlying asset price ST is above the strike price K at expiration, and zero otherwise. Its payoff function is a step function, a discontinuous leap from 0 to 1 at a point K. While Riemann integral can sometimes handle simple discontinuities, it becomes increasingly fragile as payoff structures grow more complex. Part-dependent options, barrier options, and other exotic derivatives can have payoffs that are highly irregular and pathological from the perspective of Riemann integral. The more profound failure of the Riemann integral, however, lies in its poor interaction with limits of a function. A robust theory of finance, particularly one that models asset prices in continuous time, must be able to handle limiting processes. For instance, a continuous time model is often conceptualized as the limit of a discrete time model as the time steps shrink to zero. This requires a theory of integration where the limit of the integrals of a sequence of functions is equal to the integral of the limit function. The Riemann integral provides no such guarantee under general conditions. The limit of a sequence of Riemann integral functions may not be Riemann integrable itself. The inadequacy of Riemann integral is therefore a direct impediment to the development of a rigorous theory of financial valuation. A new, more powerful engine of integration is required, one that can handle the discontinuities and complex payoffs of modern financial instruments, and most importantly, possesses the robust convergence properties necessary to serve as the foundations for stochastic calculus. Now, let's look into the tools of modern probability. The demonstrated failures of classical probability and Riemann integration created a mathematical vacuum at the heart of quantitative finance. To fill it, the field turned to the more abstract and powerful frameworks of measure theory, developed in the early 20th century by mathematicians like Henri Lebesgue and Émile Borel. This was not the adaptation of an overly complex tool for its own sake. Rather, it was the systematic construction of a new mathematical language precisely engineered to overcome the limitations of the old language. This new language is built upon three foundational pillars: the sigma algebra, which defines the universe of possible events, the probability measure, which assigns likelihoods to those events, and the Lebesgue integral, which provides a robust definition of expectation. Now, first look into the sigma algebra. Before one can assign probabilities, one must first define precisely what constitutes an event. In a simple experiment, like a coin toss, the events are trivial subsets of the sample space, heads or tails. But for a continuous sample space, like the set of all possible stock prices, where the sample space is somewhere around 0 to infinity, the notation becomes far more complex. It turns out to be mathematically impossible to construct a consistent probability measure that can be assigned to every conceivable subset of the real numbers without sacrificing the desirable properties like translation invariance. The solution is to restrict our attention to well-behaved collection of subsets, and this collection is known as the sigma algebra, denoted by F. A sigma algebra is a mathematical formalization of a consistent event space. It represents the set of all reasonable questions one can ask about the outcome of an experiment, questions to which well-defined probability can be assigned. The subsets contained within the sigma algebra are called the measurable sets, or in context of probability, events. For a collection of subsets F of a sample space to be sigma algebra, it must satisfy three deceptively simple axioms. The first one is the entire sample space must be in the collection. This ensures that did some outcome occur question is a valid one. Since a sigma algebra is closed under complements, this also implies that the empty set is in F. The second axiom is that it must be closed under complementation. If a set A is in F, then its complement AC should also be in F. The third axiom is that it must be closed under countable unions. If A1, A2, and so on is a countable sequence of sets in F, the reunion must also be in F. These axioms are not arbitrary. They are the minimal requirements for logical consistency. If one can assign probability to an event A, it is logically necessary to be able to assign a probability to an event of not A. Similarly, if one can assign probabilities to a sequence of events, one must be able to assign a probability to their union. The sigma algebra ensures that the collection of events is closed under these fundamental operations of logic and set theory. This pair, consisting of the sample space and the sigma algebra of its subsets, is a measurable space. It provides the foundational structure upon which probability can be built, a set of all possible outcomes. With a well-defined measurable space in hand, the next step is to actually assign probabilities to the events in F. This is the role of a probability measure. A function P that maps each event in F to a number in the interval is called the probability measure. This triplet is known as the probability space, and it is the cornerstone of modern probability theory. Now let's look into the axioms of the function P. The first one is that it should be non-negative. For any event A belongs to F, its probability is non-negative, that is P of A should be greater than or equal to 0. The second axiom is that it should have a unit measure. The probability of the entire sample space is 1. This axiom formalizes the idea that some outcome must occur. The third axiom is countable additivity. For any countable sequence of pairwise disjoint events, A1, A2, and so on, the probability of the reunion is the sum of the individual probabilities. This third axiom is the most powerful and is the direct counterpart to the closure under countable unions property of the sigma algebra. It is what allows the theory to handle infinite sample spaces and limiting arguments with rigor. This axiomatic approach of Kolmogorov's was a paradigm shift. By defining a probability space as a specific type of measure space, he instantly unified discrete and continuous probabilities with a single coherent framework. More importantly, he demonstrated that nothing more than the existing tools of measure theory was required to put probabilities on a firm mathematical foundation. This meant that the entire powerful arsenal of real analysis, including the sophisticated theorems on integration and convergence, could be directly imported and applied to the study of probability. Now let's look at the final pillar of measure theory, the Lebesgue integral. This framework is a new theory of integration that resolves the failures of the Riemann integral. The Lebesgue integral, defined with respect to the probability measure P, provides a robust general definition of the expected value of a random variable. The conceptual leap made by Lebesgue was to reimagine the process of integration. Instead of partitioning the domain into vertical strips, the Lebesgue integral partitions the range of the function into horizontal slabs. This is simply the value of weighted sum of probabilities, the familiar definition of expectation from elementary probability. The integral of a more general non-negative random variable is then defined as the supremum of the integrals of all simple functions that are less than or equal to it. This construction provides the unifying definition of expectation that finance requires. For a discrete random variable, the Lebesgue integral reduces the standard summation. For a continuous random variable, it provides a rigorous integral definition that is more powerful than the Riemann's. This allows discrete time models and continuous time models to be understood as specific instances of the same underlying theory. The true power of Lebesgue integral lies in its analytical properties. It can integrate much broader class of functions, including the discontinuous pair of functions. More critically, it is accompanied by powerful convergence theorems, namely monotone convergence theorem and the dominated convergence theorem. These theorems provide clear and relatively mild conditions under which one can interchange the order of limits and integration. Having established a static single period framework for probability, the next challenge is to model the evolution of financial markets through time. Asset prices are not static, they're dynamic random processes. The true power of the measure-theoretic framework is revealed in its ability to provide the language tools necessary to describe these dynamics with mathematical rigor. First, let's look into stochastic processes and Brownian motion. A stochastic process is the mathematical object used to model a system that evolves randomly over time. Formally, it is a collection of random variables, xt, indexed by a time partner t, all defined on the same underlying probability space. For each point in time, t, xt is a random variable representing, for example, the price of a stock. For each outcome, the function represents a specific possible path or trajectory of the stock over time. While the concept is intuitive, its rigorous definition, especially for continuous time, is deeply reliant on measure theory. Defining a probability distribution over an infinite dimensional space of functions is a non-trivial task. The Kolmogorov extension theorem, a cornerstone of advanced measure theory, provides the precise conditions under which a consistent family of the finite dimensional distributions can be extended to define a full stochastic process, guaranteeing its mathematical existence. The foundational stochastic process in finance is Brownian motion, also known as Wiener process, denoted by WT. Its key properties are continuous paths, independent and normally distributed increments, and these capture the essence of the random walk hypothesis of efficient markets. Modern quantitative finance overwhelmingly models asset prices using the stochastic differential equations, which describe the infinitesimal evolution of the process. The most famous of these is the geometric Brownian motion, which assumes that the stock price ST follows the following stochastic equation, which is d of ST is equals to mu of ST dt plus sigma ST dWt. Here, the change in the stock price dST over an infinitesimal time interval dt is composed of two parts, a deterministic drift component UST dt representing the expected return and a random diffusion component sigma ST dWt representing the volatility-driven uncertainty, where dWt is the increment of a Brownian motion. The entire field of stochastic calculus, which provides the rules for manipulating such equations, is built upon measure-theoretic foundations of probability and integration. Financial markets are not just random. They are systems in which information is continuously revealed and incorporated into prices. A realistic model must capture this dynamic flow of information. Measure theory provides two elegant and powerful concepts for this purpose: filtrations and martingales. A filtration, denoted by sequence of ft, is a sequence of increasing sigma algebras, fs, which is a subset of ft, for all s less than t. Each sigma algebra ft is a sub-sigma algebra of the main event space f and represents the total information available to the market participants up to and including time t. The condition fs, subset of ft, formalizes the intuitive notation that information accumulates and is never lost. An event A is in ft if by the time t it is known whether or not. This abstract construction transforms the vague concept of information into a concrete mathematical object, allowing for rigorous definition of other crucial ideas. For example, a stochastic process denoted by xt is said to be adapted to filtration if for every t, the value of xt is known at time t. This is a minimal consistency requirement for any model of an observable asset price. Building on the concept of filtration, we can define a martingale. A martingale is an adapted stochastic process that satisfies the following conditions. The conditional expectation of the future value of the process given all information available today is simply its current value. A martingale is the mathematical formalization of a fair game. In a fair game, there is no bias. The best forecast for the future is the present. The concept of martingale is absolutely central to modern finance because it is mathematically equivalent to the economic principle of no arbitrage. In an arbitrage-free market, it should be impossible to construct a trading strategy that generates a risk-free profit. The mathematical expression of this principle is that the discounted price process of any traded asset must be a martingale under a special probability measure. This connection forms the basis of the fundamental theorems of asset pricing and is the key to the entire theory of risk-neutral valuation. The machinery of filtrations and martingales provides the language to state and prove these theorems, forming the theoretical core of modern pricing theory. The theoretical machinery developed in preceding sections, the probability spaces, the Lebesgue integral, the stochastic processes, and the martingales, culminates in a powerful and elegant solution to the central problem of quantitative finance: how to determine the fair price of a derivative security. The solution involves a profound conceptual shift, moving from the real world of forecasting to an artificial world of constructing purely for pricing. This transition is known as change of measure, and it is the mathematical engine that derives all modern pricing models, from Black-Scholes to the most advanced models for interest rates and credit risk. To price an asset, one must account for both the time value of money and the risk associated with the future payoffs. A naive approach might be to forecast the expected future payoff and discount it back to the present. However, the current discount rate to use is not obvious. Investors are typically risk averse and demand compensation for bearing risk. A risky asset, therefore, must offer a higher expected rate of return than a risk-free asset like a government bond. This additional expected return is the risk premium. The appropriate discount rate for a risky cash flow should reflect this premium, but the size of the risk premium is unobservable and investor-specific and notoriously difficult to estimate. This challenge reveals the need to operate in two distinct probabilistic worlds, defined by two different probability measures. The first one is the physical measure P. This is the real world probability measure. It describes the actual objective probabilities of the future events based on the best available data and models. Under the measure P, the expected instantaneous return of a risky asset is greater than the risk-free rate. That is, the difference U minus R represents the risky premium. The physical measure is used for applications that require realistic forecasting, such as risk management, portfolio optimization, and economic simulations. Now, let's look at the second measure, which is the risk-neutral measure, Q. This is specially constructed artificial probability measure used exclusively for asset pricing. It is also known as the equivalent martingale measure. The defining property of the measure Q is that under it, the expected return. The genius of this approach is that sidesteps the problem of determining the correct risk premium. Instead of calculating an expected payoff using real-world probabilities and then struggling to find the correct risk-adjusted discount rate, we perform a change of measure from P to Q. This change adjusts the probabilities themselves to account for risk. Once in the risk-neutral world, pricing becomes remarkably simple. We calculate the expected payoff using the risk-neutral probabilities EQ and then discount this expectation at the simple known risk-free rate R. This entire framework rests on the fundamental theorems of asset pricing. The first fundamental theorem states that market is free of arbitrage opportunities if and only if at least one equivalent risk-return measure Q exists. The second theorem states that an arbitrage-free market is complete if and only if the risk-neutral measure is unique. These theorems provide the profound link between economic principle of no arbitrage and the mathematical existence of risk-neutral measure. The conceptual leap from the physical measure P to the risk-neutral measure Q is powerful, but it requires a rigorous mathematical mechanism to be operational. The Girsonov's theorem is this mechanism. It is the pivotal result from stochastic calculus that provides the formal result for translating between the two probabilistic worlds. If we recall the GBM model for a stock price and the physical measure P, it is dSt is equals to mu into St into dt plus sigma into St into dWt. The goal is to find a new measure Q under which the dynamics are risk neutral. That is, dSt is equals to R into St into dt plus sigma into St into dWtQ. Comparing the two equations, we see that the Brownian motions under the two measures must be related. Specifically, the drift must change from mu to R. This implies a relationship of the form dWtQ is equals to dWtP plus mu minus R by sigma into dt. The term u minus R by sigma can be coined as theta, is known as the market price of risk. It represents the excess return per unit of risk or the volatility. The equation above suggests that the Brownian motion under Q is simply the original Brownian motion P plus a deterministic drift term related to the market price of risk. Girsonov's theorem provides the formal justification of this transformation. It states that if we start with the Brownian motion WTP under measure P, we can define a new equivalent Q such that the process WTQ is equals to WTP plus integral of 0 to t theta s into ds. And this is a standard Brownian motion under Q. The theorem provides the explicit formula for the transformation key, which is known as the Radon-Nikodym derivative of Q with respect to P, denoted by dQ by dP. This derivative, often called the Girsonov's kernel or density process ZT, is a martingale that connects the expectations under the two measures via the relation EQ of x is equals to EP for a random variable x at time t. A crucial consequence of Girsonov's theorem is that the change of process alters the risk of the stochastic process. This is intuitively correct and vital for the theory. Volatility is an intrinsic property of the asset's random fluctuations. independent of the investor's risk preferences. The drift, however, contains the subjective risk premium that we wish to eliminate for pricing. Gerson's theorem provides the precise tool to surgically remove the risk premium from the drift, transforming it to a risk-free rate while leaving the underlying volatility structure intact. It is the rigorous mathematical engine that powers the entire risk-neutral pricing framework. The culmination of this entire theoretical journey, from the foundations of measure theory to the dynamics of stochastic processes and the change of measure, is the universal risk-neutral pricing formula. The single elegant equation that states that arbitrage-free price Vt at time t of any derivative security with a payoff Vt at future time t is the expected value of its future discounted payoff calculated under the risk neutral measure q and conditional on the information available at time t. This is how it is written as a formula. This master formula is a dense synthesis of every measure theoretic concept we have developed. The expectation EQ is a Lebesgue integral with respect to the risk neutral probability Q. The payoff Vt is a random variable, typically a function of an underlying stochastic process. The conditioning of the filtration Ft formally incorporates all the information known up to the pricing time t. The existence of the measure Q is guaranteed by the economic principle of no arbitrage, as established by the fundamental theorems of asset pricing. The ability to practically compute this expectation by switching from the real world measure P is enabled by the Gerson's theorem. The celebrated Black-Scholes model is most famous and direct application of this formula. The model assumes the underlying asset ST follows a geometric Brownian motion. To price a European call option with payoff given by max function of ST minus K, 0, one simply applies the risk-neutral pricing formula. Under the risk-neutral measure Q, the process for ST has a drift equal to the risk-free rate R. This implies that ST has a log normal distribution under Q. The pricing problem then reduces to the concrete task of calculating the Lebesgue integral of the discounted payoff function over this log normal distribution. The execution of this integral yields the famous Black-Scholes formula. This logical progression from axiomatic probability and measure theory through stochastic analysis to the risk-neutral pricing formula is not merely one way of approaching finance. It is a standard pedagogical and professional paradigm. It is the foundational language in which the story of modern finance is written. The journey from the simple counting exercise of classical probability to the abstract machinery of measure theory represents a profound intellectual evolution driven by the practical necessity of modeling complex financial realities. This report has traced this path, demonstrating that measure theory is not an esoteric academic pursuit, but the very grammar of the modern quantitative finance. Its adoption was a direct response to the fundamental inadequacies of earlier mathematical frameworks. Upon this foundation, the tools to model market dynamics were forged. Stochastic processes, particularly Brownian motion, gave a language to the randomness through time, while filtrations and martingales provided a rigorous framework for modeling the flow of information and the principle of no arbitrage. The final and most powerful application of this machinery was the development of risk-neutral pricing. The conceptual shift from the physical measure P to the risk-neutral measure Q, made possible by the mathematical engine of Gerson's theorem, revolutionized the asset pricing. It replaced the interactive problem of estimating the subjective risk premium with a concrete mathematical procedure, culminating in a universal pricing formula that stands as the cornerstone of the field. Ultimately, measure theory provides the single unifying framework within which every key concept of the modern finance, such as randomness, information, expectation, and value, is given a precise interconnected meaning. It is the language that allows for the rigorous statement and proof of the field's most fundamental theorems and the derivation of the most critical pricing models. Thank you.